Thanks a lot. And I love your style of like doing the introduction for the speaker, especially because a lot of people, I think, they just jump right in with things about, mixture transforms and Gelfand-Zetlin bases, and don't always try to motivate things. I'll try to motivate this. This is joint work with Marcus Appleby and Gene Kopp. And an alternative title is How to Probably Sort of Construct Sick POVMs. I'll be slightly clearer about what I mean by that later. So this is the construction in dimension 2 that Maris was just talking about. So the definition of a Seq POVM, it's a set of d squared complex equiangular lines, or equivalently a set of d squared rank 1 Hermitian projectors that satisfy this thing, that their trace inner product is 1 if j equals k, and otherwise it's 1 over d plus 1. This number pops out of the geometry if you just constrain the dimension to d and the number of different projectors to be d squared. And so what does this look like if I take a solution to this and I put it on the block sphere, then these 4 vectors here are the pure state projectors of a solution to this set of equations. And so yeah, this is pronounced C. Okay, so these are geometrically elegant. But they also have very many interesting properties. It can be shown that this number n equals d squared, the number of pure state projectors, is the maximum number of complex equiangular lines that you can have in a two-dimensional complex space. They also form a minimal complex projective 2 design. So we heard, the cardinality of these designs isn't necessarily the most important parameter for these designs, but it's still interesting to find certain minimal structures. They also saturate many other extremal criteria. So they're a maximal equiangular type frame. I'm not going to define these things. I just want to show that these things do pop up as extremal examples. And he said these things are useless in the sense that these things saturate certain extremal criteria, but as one of the questions in the last talk asked, like, well, couldn't you just do something approximate? Yeah, okay, yeah, you could, that's fine. It's still the case that it's natural. Here we have a very beautiful geometric object and a natural conjecture associated to it. It would be nice if we could construct these things, even though for practical purposes, we might be able to substitute in approximate versions of these things. So, yeah, you could do all this with approximate things, but it's still, I think, a nice question. So, it saturates the Welch bound. It's the optimal norm constant relating L2 and the Gowers U3 norm for the group Z mod D. It's an optimal POVM for quantum state tomography by some definition. You get improved rates for certain QKD schemes. You can increase the efficiency of shadow tomography using these things. Okay, so this is all great, but do they even exist? We saw they exist in D equals 2. What about in higher dimensions? In 1999, so this is a 25-year-old open problem. In 1999, Gerhard Zauner conjectured that they exist in every dimension. He actually conjectured something much stronger than this about certain symmetries that I don't have time to get into. And a lot of people, beginning with Zauner himself, have constructed examples in a lot of small dimensions. And you might think, especially if you're looking at that initial problem, you might think, well, I'll just do some kind of inductive argument. I mean, how hard can this be? I write down these vectors and I just guess the solution and then inductively prove it. Well, if you can write that out from the first 53 examples, then I'll be very impressed. Because if my title wasn't clear enough, this is still an open problem. Although I do think that we finally understand the problem. So people have constructed high precision numerical solutions in dimensions up to 193 and a small number of higher dimensions. However, there are only finitely many dimensions to date where there are known Cs. There's even a prize if you can find an infinite family. So with one exception, every known C in this example is somehow sporadic. It involves quaternions or something, so it's unclear if that will generalize. But aside from this sporadic example, every known C is covariant, I'll explain what that means, with respect to the Weil-Heisenberg group, also known as the Q-date Pauli group. So this is just the group where if I fix a d root of unity here, and then there's this extra thing which is a square root of this, which is useful to introduce for various technical reasons. It's the group which acts as shifts modulo d on the standard basis, or shifts in the phase modulo d when acting on the standard basis, and so these things generate a group. A set of coset representatives for this group modulo its center, which is how it acts when you're acting projectively on states, is given by the displacement operators. So these are familiar displacement operators. Covariant just means that I can construct one of these seeks as the orbit of a certain fixed fiducial vector. This is called the fiducial or the seek fiducial. I'll just call it pi, although you could index it with a 0. So it's just the orbit under the projective action of these displacement operators, and that's going to generate the seek. And then because I've fixed this, I fixed this standard basis, and then I fixed this definition of the Heisenberg group. If I look at the unitary equivalence classes under conjugation of these things, they actually split into equivalence classes based on what's called the extended Clifford group. This is like the Clifford group together with one additional operation, which is complex conjugation in the standard basis. Okay, so when I talk about seeks, I'm talking about Weil-Heisenberg covariant seeks. And I only care about understanding this problem up to this equivalence class, because that's, this equivalence relation is kind of the trivial symmetries that you get. And moreover, there's a couple other pathologies that happen when the dimension is 2 or 3. I'm going to, henceforth without comment, make these restrictions. By the way, interrupt me actually if you have questions. It's the last talk, why not? Okay, so our first main result is a construction of seeks. However, so it provably yields seeks if we assume 2 refinements of what are called the Stark conjectures, and I will give the barest, the thinnest possible. I mean, I don't fully understand the Stark conjectures either, so, but I'll try to give you some intuition for what they're trying to say. So these 2 conjectures, one of them is a standard refinement of the Stark conjecture due to Tate from the early 80s. And so I'll call that the Stark-Tate conjecture. The other one is called the twisted convolution conjecture, and it takes the form of a special function affinity. So the informal statement is, assuming Stark-Tate and twisted convolution, Zauner's conjecture is true via an explicit construction.
The notion of construction here is a little bit unusual because what we have to do is first construct this object that we call a ghost, and then we have to resurrect it. And we came up with this terminology because when we were first doing it, it did seem like some sort of dark magic that we had to do to bring this thing back from the dead to create this live object. And it didn't. I mean, it still is a little surprising to me that this works. But you'll see, it's not a construction which is just like a formula that you evaluate. It's a little more involved. Okay, so some terminology. If you just use this property, the defining property of these equiangular lines is that the trace inner product is constant for distinct pairs. And if you write that out together with this Weil-Heisenberg symmetry, you find that I can equivalently define seek fiducials as being rank 1 Hermitian projectors that have the following form. I just expand them in the displacement operator basis. And then I look at these new sub p's as the expansion coefficients. And they have to satisfy 2 conditions. So this pi has to be rank 1. These nus have to be complex unit phases called the overlap phases. And then because it's Hermitian, nu p times nu minus p, where the index arithmetic is always modulo d, is 1. And this boldface here is because this is a vector in ZD cross ZD. So it's like the, that's the Q-dit Pauli group modulo its center. Okay, so a long series of works that I don't have time to do justice to has culminated in showing, so, lots of people have contributed to this, notably names like Scott, Grossel, Appleby, Kopp, and many others, has, after a lot of hard work and insights, shown that there are several concrete examples where these new P's are certain special algebraic objects. So these special algebraic objects in every case are essentially Galois conjugates of powers of Stark units, which I'll explain a little bit what they are, over a number field, Q adjoins square root of delta, where delta is this number right here as a function of the input dimension. Okay? So this is just rational linear combinations of a rational plus rational times this. Okay, this is a number field. So recall, if you're not familiar with it, what Galois conjugation means. It just means there's a Galois automorphism, meaning a field automorphism of this that fixes the rational field, which is the field below it. So like sigma is an automorphism. There's a non-trivial automorphism that acts on these rational linear combinations by flipping the sign of root 2. Okay, complex conjugation over Q adjoin I is another example of a Galois automorphism that you're definitely familiar with. But you can do these other forms of automorphisms as well as over other fields, over number fields. So, but what are these Stark units and why are they special? So I definitely don't have time to explain this in this talk, but the basic idea, and you may not understand all the words that I'm going to say, that's okay. This is just to give you a flavor. The basic idea is that, and this is closely related to Hilbert's 12th problem as well. So there's an open Hilbert problem underlying this. There are certain special points of transcendental functions where at those special points, the function is actually algebraic, okay, or the function value at that point is algebraic. So if I give you a transcendental function, right, generic points don't satisfy any polynomial equations, but at these special points they do. And the form of these conjectures relates certain properties of zeta functions. So you've heard of the Riemann zeta function. There are other more general zeta functions involving more general concepts of integers and primes, prime ideals, and algebraic integers. So it relates certain properties of zeta functions or L functions and arithmetic properties of these associated number fields. So it connects two seemingly distinct things. One side there's analysis, and one side there's arithmetic. Okay, and so this is offered as a kind of an attempt to solve this Hilbert problem by showing. So Hilbert asked whether or not we can generate entire number fields based on these special points of transcendental functions. Essentially, the only known cases where this is solved are where the underlying number field is the simplest possible number field, the rational number field. And in that special case, the transcendental function is the exponential map, e to the 2 pi I z. And whenever z is a rational number, you generate a number field, which is like these cyclotomic number fields, which are the abelian extensions of this. If you don't know what those words mean, it's okay. And the other case is when I have an imaginary quadratic field, n is positive here, so this is an imaginary quadratic number field. And these are generated by torsion points of elliptic curves with complex multiplication, big words. But this case is understood. Already, presumably the next simplest case is if I replace this negative n with positive n. That's called the real quadratic case, and this is in fact open. Hilbert's 12th problem asks for this solution for this in general. And Stark gives some sort of conjectural approach to trying to solve this in terms of things called L functions or derivatives of L functions. Okay, so based on this prior work by all these people, our goal is to do the following, okay? Our goal, so I mentioned that, the prior work showed that in many special cases, we can construct seeks by taking Galois conjugates of these certain special Stark units, okay? So based on that, that motivates the following definition, or I claim it motivates it. Probably I didn't give you enough evidence to really believe it, but take my word for it. That motivates the following definition. So this equation looks very similar to the one that I had before, where I had these complex phases here, but I've changed it a little bit now. So now I have a rank 1 matrix, which is not necessarily Hermitian. And I insist that the expansion coefficients, instead of being unit phases, they're going to be real numbers, but they're still going to satisfy this condition here, okay? And I'm going to call such an object, if I can construct one, or if it exists, a ghost, okay? And the motivation, as I said, is we expect to be able to construct these numbers using conjectural Stark units. And then we're going to be able, we hope to find this Galois automorphism, this thing that can flip the sign in this number field, so that if I act with the Galois automorphism on the ghost, I can resurrect it and build my seek P of M. There's a question.
Very quick question. What is the range of P in that summation?
It runs over the elements of D squared. It's the cosets of coset representatives of DZ squared, right? So like all the elements, all the ordered pairs of integers mod D except the 0, 0 pair, basically. Okay, so I'm not going to have time to show you a big fancy formula for this, but we have a formula for ghosts that we can write down in terms of what are conjectural Stark units. So it comes out of this special function that we define called the Shintani-Faddeev modular cocycle. And this is the Hebrew letter Shin, which is just an homage to Shintani, who wrote down a related function called the double sign function, which is sort of part of the definition of this function. It's kind of hard to typeset this, by the way. So in any case, so this thing is interesting. It has a couple parts in it. It has this parameter in it, SL2A, which is an element of SL2Z, and a parameter tau, which is a complex number. You could think of this as parameterizing like a lattice. So this function has two periods to it as well, similar to like elliptic functions. So this is closely related to Shintani's double sign function as well as Faddeev's quantum dial algorithm. It also has a well-behaved integral formula that makes it tractable for numerical calculations. So think of this as the kind of thing like you're doing some calculation in Mathematica and it spits out 2F1 hypergeometric blah, blah, blah. And you're like, oh my gosh, I don't know what that is, but I can evaluate it to whatever precision I want pretty quickly. Okay, so using the Stark-Tate conjecture and properties of this function, we can argue that this thing lives conjecturally in an abelian extension over this field here, which is what we sort of hoped for from our insights. So if this is true, then our constructed ghost is an algebraic object, and therefore it makes sense for me to apply this Galois automorphism to flip this sign. So in order to prove that our construction satisfies all the conditions of a ghost, we also need to conjecture this twisted convolution identity. This is a convolution together with this, this is a symplectic inner product here. This is a special function identity. So it sounds easy, right? All we need to do is we've got a construction for this. So I wasn't very explicit about it, but I claim that we can do that. All we need to do is just apply this Galois automorphism to this thing and we get pi and we're done. Not so fast. So we have a formula, but it's of the form of a transcendental function evaluation. And in order to apply sigma, we need to know how to represent it as a point inside a number field where sigma acts. So let me give you an analogy to understand why this is hard. Suppose I gave you the following number. Okay, so this is just a number, right? You evaluate this integral, you take the exponential, you get this number a. And I tell you, yeah, just apply the following Galois automorphism, the one that takes root 2 and flips its sign. You're going to say, what are you talking about, Steve? This doesn't make any sense. How do I even know that that thing lives in that number field or above that number field? Oh, but I promise you, suppose I even promise you that it's even in that field. How do you proceed? I give a beer to anybody who can tell me what the Galois conjugate of this number is before I get to the next click. You're so close. Wow, Graham almost got a beer. It's 1 minus root 2. He was off by 1. So one way that you could proceed is you could look at the decimal expansion of A. And you're like, well, okay, I just compute this to high precision, and it's 2.4142135. Hang on, that looks really familiar. That looks like it's 1 plus root 2. So suppose you guess this, and then you validate it by some other means. Then you could indeed conclude that sigma of A is 1 minus root 2. So this is basically what we do. We use integer relation algorithms or lattice basis reduction, like LLL algorithm, the Lenstra-Lovash algorithm. So we could just do this directly, but we developed another method. And this is what we call necromancy that uses LLL, but it works on much smaller lattices. And the recipe is roughly we compute a low precision ghost from this transcendental function evaluation, and then we use Newton's method to increase the precision. We know roughly how much precision we need from the Stark conjectures because we know what the degree of the number field is that we're trying to round into. And then we know the ghost minimal polynomial. So we know the degree of the algebraic relationship that these numbers satisfy. So we can just find that integer relation using lattice basis reduction. We can then, once we have the exact representation, we can apply this Galois automorphism. And then we've lost some information in step 2, so we can get that back by using an action of the Galois group, which we also know. And it turns out in the end, we have to run a convex optimization from compressed sensing of all places in order to reconstruct this rank 1 matrix, which was kind of interesting to me because I had previously written papers about that. So kind of came full circle. So we actually did this in dimension 100, and we found 4 seeks, 3 of which are new. And this procedure is like relatively fast. I think people use like whatever 2 CPU years or something of numerical search to find one seek through a random search in dimension 100, and we found 4 of them using this necromancy procedure. So it's kind of a miracle. We can also find, we sort of think that this is a putatively complete list of all seek solutions. So seeks seem to be classified by the following algebraic information. I see I'm running out of time. They seem to be classified by the equivalence classes of integral binary quadratic forms that satisfy some certain divisibility constraint on their discriminant. We can provably construct 1 for every class. So it doesn't seem, from the numerical work, it doesn't seem like there are any more. So we believe this is probably all of the solutions. We can also, it's kind of hard to construct the solutions themselves, but based on just understanding now what we think is an understanding of all the algebraic data that goes into this problem, we can answer certain other questions much more easily than we can actually construct the solutions. Some fun consequences of our conjectures is I can tell you conjecturally how many seeks there are in whatever dimension you want, even quite large dimensions. So, you know, in dimension 2 to the 50 plus 1, there's this many inequivalent seeks conjecturally. It would be great if somebody could prove it. And if you plot this on a graph, sorry, this got cut off a little bit, but up to 10 to the 6 here, this is how many inequivalent seeks there are conjecturally in dimension D. And actually, you can prove if you use the Brouwer-Siegel theorem that if our conjectures are correct, then the number of seeks in dimension D is omega of D. So there's a lot of seeks, actually. They're kind of all over the place. They're everywhere. So prior work tried to classify these things in this really obscure world where, like, you know, these are like specific papers where people would like write an entire paper where they proved that this seek existed in this dimension. And then they would give them names based on, like, we didn't know how to label them. So we called them like 11A and 11B. And they, you know, some of them are paired up because they live in certain fields or something. And it was like a mess. I don't think anybody really understood it. Like, we understand that now. So, we now know from this classification, we know how to associate labels, at least to the ghost side of these things, through these integral binary quadratic forms. So we sort of know the right data that goes in to label these things. People would also write these weird inclusions. Like, some of the solutions seem to be living in subfields of other solutions. And like, I mean, no, you know, 35 B, C, D, G, like, what is this? So we now know that there's like a division lattice structure that comes from divisors of conductors of quadratic forms and discriminants of the underlying number fields. And the nesting property of these field inclusions comes from the real multiplication values of non-maximal orders. So this construction actually generalizes as well. So we can ask about packing R-dimensional complex subspaces, not just lines, but like R-dimensional complex subspaces. And we get similar formulas for these things. So there's examples of like rank 3 subspaces in 11 dimensions that also pack equally and things like this. And these things also generate other abelian extensions of other number fields. So that's all I wanted to say. So it's possible to get a direct formula for seeks. So there's a bunch of open questions here. Is it possible to get a direct formula that doesn't have to do this weird necromancy thing? Are there non-Weil-Heisenberg covariant seeks beyond just this one sporadic example that I mentioned? Can we prove this twisted convolution conjecture? Do we generate all the abelian extensions of these real quadratic fields from this? If so, that would be very interesting. We can prove that we can generate a constant fraction of them in an asymptotic density sense. But we can't get all of them, it seems. And if breakthroughs in algebraic number theory are actually needed to prove seek existence, it would be nice to pursue non-constructive proof techniques to try to resolve this question. I'm somewhat hopeful that within the next 5 years, we'll be able to prove the existence of an infinite family of seeks, but it still seems rather difficult. So thank you for your attention. And I just want to flash for the YouTube viewers all the citations that I had as well. So, freeze frame that and go read these papers by these smart people. So with that, thank you very much.
Any questions to the speaker?
Does this twisted convolution conjecture sort of smell to you like hard, like Stark conjectures, or just something you can't prove yet?
I go back and forth. Sometimes I think it's just something I wasn't able to prove because I wasn't clever enough. I wouldn't say that I've tried my absolute hardest to prove it, but on my bad days, I look at it and I think it involves really understanding some deep number theory and the interplay between multiplication and addition, and it looks hard. So I don't know. I mean, I wouldn't be that surprised if somebody came up with a relatively simple proof, but I also sometimes feel like it could be hard. It's difficult to know. I think more people need to look at it and think about it.
Any other questions? Oh, yeah, there's one.
Yeah, could you show us actually that twisted convolution conjecture again?
Yeah, so these things are the units that we construct from this formula that I didn't give.
That was my question.
And then this is a root of unity, and this is a symplectic inner product.
I was also wondering, so, when you have a hard problem, you can, in mathematics, what people do, they make it harder, and then maybe it's easier to prove. And, also, if you want to make it in any way practical, it makes sense to conjecture that there is like efficient quantum circuit for doing this measurement. And so, could that be an angle could that like add more structure to the problem? That like to say that, not only this thing exists, but there is an efficient circuit. And also like, for example, you didn't talk about these ladders of dimensions. And so like maybe, if you know the circuit for one dimension, then you can recurse in this ladder or something like this.
Yeah, no, that's a great question. I haven't thought enough about efficient circuits for these things. I think that's a great question. I've thought for a while that an avenue to proving this might be to do some kind of induction on these towers of dimensions where the sort of higher solutions that live in the same field are like harmonics or something of the lower dimensional seeks. But I've never had any success. I mean, I should say I haven't thought super hard about it either, but like I've never felt like I had an idea for how to approach it. So I think these are great questions, but I don't really have any insights.
Okay.
Fascinating. It's a small question. How does using LLL to identify the like quadratic irrational compare to like a continued fraction expansion, and then recovering from the period?
Yeah, I mean, if it's a quadratic, so the degree isn't always quadratic. It depends how we do it. Like in one of the ways that we do it, it's not always a quadratic. For quadratics, you could just use a continued fraction expansion. I'm not actually sure what the difference is because you have to go out to see the period of the continued fraction, which could be quite large.
Yeah, I think both can probably be exponentially inefficient.
The continued fraction expansion approach. Yeah, that's right. So I don't know if it's, I think it might be more efficient. You basically need to go out to the degree. I mean, you should be able to get on the order of the number of digits of precision that you need before you see that integer relation times some prefactor, like, I don't know, factor of 2 or something. And then you should be able to recover the integer relation. We also, sometimes it turns out to be helpful if we can find slightly higher degree polynomial relations as well, because we retain more information about the original solution rather than pushing it all the way down to the quadratic field. And so we run LLL over polynomials whose degree is the class number of the number field, which is a little bit higher, but it still converges and is done with moderate precision. Like all of this stuff, like I wrote code in Julia to do this, and it's like pretty fast. So,
thank you.
All right.
Yeah, I should also stress, like, this is not like 500 pages of interuniversal Teichmuller theory where we're just like, this conjecture implies this conjecture, and I now make this stronger conjecture. Like, I have Julia code that does this, so it's not just. Yeah.
All right. I think all the hardcore SIGPM fans want to go and get some dinner, so let's wrap it up.